Let's look at this practice problem. We're trying to determine part A, will a precipitation occur? Now we've got a 0.022 molar silver nitrate solution. Whenever you see that capital M, it means molarity. It means moles of the substance divided by liters of solvent. And that means that we're talking about an aqueous solution. Silver is a +1 transition metal, and nitrate is a polyatomic ion with a charge of -1, and this is a spectator ion. So let me just emphasize that here. The reactive species in silver nitrate is going to be silver ion. We've got sodium carbonate. Now again, it's a 0.0014 molar solution of sodium carbonate. So we know that sodium carbonate is aqueous because of that capital M designation. Now, in this formula, there are two sodium ions. Sodium is in group 1 of the periodic table, so we know its charge is +1. And carbonate is a polyatomic ion with a -2 charge. Sodium is a spectator ion. So let me just emphasize that the reactive substance present in sodium carbonate is the carbonate ion. Okay? Let's now write out a precipitation reaction. So silver ion is going to buddy up with carbonate to give silver carbonate. Now you might not know what the formula of silver carbonate is, so we need to write out the charges here. Okay, and crisscross or just think about it, right? So this has a charge of -2, so we need a total of a +2 charge to counteract that. So we're going to need 2 silver ions in the formula. And this is presumably going to be a solid substance that's not very soluble. Now we balance this chemical equation by putting a 2 in front of this, okay? Now, if we want to write a Ksp, we can do that as well. We would write the solid substance on the left, and we would write the products on the right. Okay, and we could write an equilibrium expression and everything else, but let's hold off on that, just so I don't write over very important areas in this document. I'm going to reserve this space here for future writing. For now, remember what we talked about previously. When you mix two solutions, you're going to have to do a dilution problem first. Okay, and we're interested in primarily these two substances, okay? Silver ion and carbonate. Now, for solving part A. For part B, we're not only going to solve for silver ion and carbonate, but we're also going to solve for sodium ion and nitrate ion, and we'll do that later, okay? So for now, let's go ahead and do the dilution, okay? So we want to do 2 calculations. One is to figure out, hey, what is the initial concentration of silver ion when the water from sodium carbonate mixes with the silver nitrate, okay? So we want to use the dilution formula here, and we're solving for M2. Okay, and we want to plug in the initial molarity of silver nitrate. That's this quantity here, 0.022 molar. The volume of the silver nitrate is this quantity here, 45.00 milliliters. And V2 is going to be the total volume. The total volume is going to be the additive of these two solutions. So it's going to be the 45 milliliters plus the 13 milliliters. Okay. Milliliters is going to cancel, and you're going to be left with the molarity afterwards. So let me go ahead and do this on my calculator. Zero 0.017 molar. Okay, and I'll put a little label on that. That's the silver ion concentration. Okay, and that's M2, or that's the initial concentration. So let me go back up to my ice table here, and I'm going to plug in right here 0.017 molar. Okay. Now, let's go ahead and do the same thing for carbonate. Carbonate is the other reactive chemical. Let me try to put it in over here on the right. Okay, so again, we want to figure out what is the carbonate ion concentration initially when the sodium carbonate solution is diluted from the water from the silver nitrate solution. So we use that same relationship again. And what we want to do is plug in these values. So the initial concentration is different color pen here. Sodium nitrate is 0.0014 molar. The volume of the sodium carbonate is 13 milliliters. And the total volume is this same quantity as before. Milliliters cancels, and I'll go ahead and do this on my calculator. Oops, 0.0014 times 13, divide 45 plus 13. I'm using parentheses for those. Okay, on my calculator, I'm getting 3.1 times 10 to the minus 4 molarity carbonate. Okay, and what I can do here is express this as a decimal if I wanted. I'm just going to leave that. Okay, so I have these two concentrations. All right. Now, remember what we do for to figure out if there's a precipitation or not. We write out the equilibrium expression for this chemical reaction, and then we plug in the initial values that we've since calculated, and we see if Q is larger than K or less than K. Okay? So we say that the Ksp, right, is equal to products over reactants. We've got a silver ion. Since we got two of them, we need to square the silver. And we have a carbonate ion, okay, and that's Ksp. Now, these are equilibrium values normally that you plug in to calculate the equilibrium constant. But we're going to calculate Q. It has the same expression, but remember again that we plug in the initial concentrations before a proposed chemical reaction to see what this is equal to, okay? So we plug these in. Don't need to worry about units. And let's see what I get on my calculator. Okay. 17, square that, times 3.1, 10 to the minus 4. Okay, so that's 8.959. I'm going to round this off to 9.0. 10 to the minus 8, okay? Now what I'm going to do is refer to a table of data, and we're looking for Ksp values. Okay. At the moment, I'm using a different textbook, but I'm going to flip to the appendix and find that value here for us so we can complete the problem. Okay. So Ksp values for silver nitrate solubility product constants. Silver carbonate is 8 times 10 to the minus 12. Okay. All right. And it looks like Q is less than that, so precipitation will not occur. Okay. We have 9. Oh, wait. I'm mistaken here. I was ignoring the exponents there. This is 9 times 10 to the minus 8, which is a huge number compared to 10 to the minus 12. Q is greater than Ksp, so it means that precipitation will occur. All right. Now, what we want to do here is grab our ice table to solve for part B. Now, let me come back up to the part B. Part B asks us to calculate, we'll do underlined here in blue first, the sodium ion concentration and the nitrate ion concentration. And then we'll do the silver ion and carbonate ion. Now, we know that there's going to be a precipitation, so the concentration of the ions is going to decrease as the solid forms. And so we need to compute, well, how much is left after that chemical reaction. And I like to use an ice table to set that up. So let's just grab this whole thing here. Okay. Well, I can move it down, but I can't cut it. So let's go ahead and do part B. Now we need to know the concentration of sodium ion, okay? And remember, we're mixing silver nitrate. And here's the relevant data. We have 45 milliliters of 0.022 molar silver nitrate. Okay. And so there's no sodium in any of these formulas. And we're mixing sodium carbonate. And we're mixing 13.00 milliliters of 0.0014 molar sodium carbonate. Okay? And so what we do is we basically are going to just calculate the concentration of sodium from the, dilution formula here. Okay? Now, the first thing we want to do is we want to convert from moles of sodium carbonate to moles of sodium ion. The reason for that is because of this coefficient of 2. Okay? So let's go ahead and do that. We have 0.0014 moles per liter of this sodium carbonate. And because of that chemical formula, we have 2 moles of sodium ion per mole of sodium carbonate. Okay? So the moles of sodium carbonate cancels, and you're left with 0.0028 molar sodium ion. Okay? Notice how molarity is basically just moles per liter. Okay, but I'm drawing it out in case you kind of forget that from the previous chapters. So now what we want to do is apply the dilution, okay, because this solution becomes diluted from the water, the 45 milliliters of water that's present in silver nitrate. So you set that up as before, okay? And we're solving for the final molarity of sodium ion. And this value is not going to change whether or not precipitation occurs because sodium ion is a spectator ion and does not react, okay? So the initial molarity here is 0.0028, which we just calculated. The volume of this sodium carbonate is 13 milliliters. And I'm going to divide that by the 45 plus 13. Okay. Milliliters cancels, and you're left with molarity in the final answer there. So let's see what my calculator shows. Oops, I forgot to put parentheses. I might have messed that up. Nope. Okay, so that's the sodium ion concentration. I'm getting 6.3 times 10 to the minus 4 molarity. Okay. The nitrate ion is done in a similar way. Okay. So remember again that we're mixing 45 milliliters of 0.022 molar silver nitrate. Now there's just a 1 there as a coefficient, right? So that's the same thing as silver ion. And we're mixing 13.00 milliliters of whatever molarity sodium carbonate. So here, because the coefficient is 1, we can just jump right into the dilution. And not too much to talk about here. So again, milliliters cancels, and let's get this on our calculator here. All right, and I'm getting 0.017 molarity, and that again is a nitrate ion, okay? Now these are the spectator ions. We can just calculate their concentration from the dilution formula because there's no chemical reaction. Now, what we want to do for a concentration of ions after a precipitation step 1 here is to assume the reaction goes all the way to the right. And we're talking about the precipitation reaction. Okay, and we calculate moles. Okay, and maybe I'll just do an ice table just to organize it since we're kind of getting more familiar with that. So the reaction we're talking about is, two silver ions are going to collide or combine with carbonate ions that are aqueous and floating around, and eventually there's a crystalline substance that forms large enough to scatter light and looks visible to the naked eye and precipitates out from solution. Okay, and what we want to plug in here is the initial molarities, actually the initial moles of substances here in the material. Okay, so what we do is we calculate moles. Of our starting ions. So we have, for silver ion, recall again that we have 45 milliliters of 0.022 molarity. So 0.022 moles per liter times 0.04500 with all those sig figs is going to be equal to 9.9 times 10 to the minus fourth moles of silver ion. Okay, so we're going to plug this in right here. Okay, and we want to do the same thing with carbonate. So with carbonate, recall that we have 13 milliliters of 0.0014 molar sodium carbonate. We have a lower volume and a lower molarity, so I suspect or hypothesize this is the limiting reactant. So let's go ahead and do this. 0.0014 moles per liter of sodium carbonate or carbonate ion times 13 milliliters is going to be equal to 1.82 times 10 to the minus 4. Okay, so you can see how these two numbers, this is much less. Okay, even after you divide by 2 and you figure out what's the limiting reactant, this is still more than this. Okay, so this is going to be our limiting reactant. So let's write that up here, and I'll explain that a little bit better. So this is 1.8 times 10 to the minus 4. Okay. All right. Now, step 4 is to figure out the limiting reactant. You do that by taking the moles that you calculated and you divide by its coefficient. Okay? And the lower the number is the limiting reactant. So we had 9.9 times 10 to the minus 4. And in this chemical reaction, it requires 2. Right? So you want to divide that by 2 and get the number. Over here for carbonate, so this is for the silver ion, this is for carbonate. You want to take this guy here and divide by 1. So 9.9 divided by 2 is, 4.95. I'm going to round this off to 5.0. Okay. And this one is the lower numbering, so it means that this is my limiting reactant. Okay? CO3 2 minus is the limiting reactant. Okay? And so we use this in the ice table. So we come up here, switch over to green, and this is all going to go away completely. And over here, remember, because of that 2, we're going to lose 2x, right? Minus 2x. And this is minus x. So we're going to have 2 times that amount. Okay. And over here, we're going to have plus x, right? We don't care really because it's a solid. Okay. And we go ahead and add the columns, remember? So this comes out to be 0. And then we'll do the math on the left with the silver ion. So 9.9, 10 to the minus 4. And we want to subtract 2 times 1.8, 10 to the minus 4. Okay? And that gives us 6.3 times 10 to the minus 4. Okay? So pretending the reaction occurred all the way to the right we would have no carbonate, and we would have all of this silver ion. Okay? Now, we can calculate the amount of silver ion and carbonate, okay, using the common ion effect approach. Okay. So generally speaking, we assume that Ksp is small. We can assume that the silver ion concentration is going to be this amount here, 6.3 times 10 to the minus 4. Plus x being small anyways. And then we can use the common ion approach. So basically the Ksp, which we've mentioned, is silver ion times carbonate. Okay. And we know what the Ksp is. I said it was, that was a while ago we discussed or used that. Ksp is 8.8 times 10 to the minus 12. Okay, and that's going to be equal to 6.3 times 10 to the minus 4 squared times carbonate. Okay, and we solve for carbonate. And don't forget to square your terms, so I'll just do the math and algebra and arithmetic here on a calculator. And I get the value of 2.0 times 10 to the minus 5th molar. Okay. Now we're going to talk a little bit more about the common ion effect in the next lecture, but this is basically how you would do that. Okay. It all comes down to this precipitation reaction. The limiting reactant gets completely used up and it becomes 0 initially. And this is 6.3 times 10 to the minus 4. And that's huge. And that's your answer for the reagent in excess. And what you need to do is apply the common ion effect to calculate the molarity of the other remaining guy.